All right, so we're going to go back real quick and look at one of the first examples that we did. We had the function g of x equals 4x plus 6, and we found its inverse to be x minus 6 divided by 4. So look at what happens. We talked about a little earlier that inverses undo each other, right? So look at what happens if I plug a value into g. Let's say I plug in 1, right? So g of 1 equals 4 times 1 plus 6. So g of 1 is equal to 10. We agree? All right. So what the inverse does is, like Jazz said, I think it switches the x and y value, right? I plugged in this x value and I got this y value out. What my inverse function does is takes the y value and it's going to give me the x value back out. So if I plug 10 into g inverse, what do I get? 10 minus 6 is 4. 4 divided by 4 is 1. Right? So the inverse, it'll take the y value on and give me the original x value back out. For this reason, if you remember a couple of sections ago, we talked about the composition of functions, plugging one function into another. So if you think about composing these two functions, if I take my inverse and plug it in for x, what do you think I would get back out? Hmm? Well, so I did essentially just do that, right? But backwards. I took g and I plugged it into g inverse. What did I get back out? I got the x back out, right? If I take my original function and I plug that into my inverse function, I'm going to get that original x value back out. Same thing if I took the inverse. If I take 1 and plug it back into my original function, I'm going to get the original x value back out. Right? It makes a little cycle. So if I plug the inverse into the original function, compose them, or vice versa, I'm going to get the original x value back out. We looked at it with numbers, but if I don't put any numbers in it, if two functions are in fact inverses, when you compose them, you will get x back out. This is a property of inverse functions. So if I have g and I plug in g inverse of x, I will get x back out. Likewise, if I do the opposite direction, if I take g and plug it into g inverse, then I'll get x back out. Okay, this is only true for inverse functions. So if I have two functions and I want to know for certain that they are inverses of each other, I'll compose them. If I get x back out, then I know they're inverses. If I don't get x back out, then they are not inverses. Okay, so let's try it. We already know these are inverses, but we're going to try it using this example. So I'm given g of x equals 4x plus 6, and we already know they're inverses, so I'll say g inverse equals x minus 6 over 4, and I want to use compositions to determine if they are inverses. So I'm going to compose them. I'm going to do it both ways. I'm going to do g with g inverse and then g inverse with g. And if I get x both ways, then I know they are inverses. So first, I'm going to take g and I'll plug in G inverse of x. Remember what that means. I'm going to take G inverses on the inside. So I'm going to take G inverse and plug it in for the x on G. So G says 4 times x plus 6. So I'm going to have 4 times G inverse, x minus 6 over 4, plus 6. Right? Function still looks exactly the same, except instead of having x, I have G inverse. Now I'm just going to break it down and simplify. I have 4 times x minus 6 over 4. A little bit of algebra. My 4's will cancel out. I get x minus 6 plus 6. The negative 6, positive 6 cancel out, and I end up with just x. Now, I want to make sure that wasn't just a fluke, and I want to do the composition the opposite direction. So I'm going to take G now and plug it into G inverse. All right, so now G is what's on the inside. So I'm going to take G inverse, and I'm going to plug G of x into the x on G inverse. So instead of x minus 6 divided by 4, I'm going to have 4x plus 6 minus 6 over 4. We okay with that? Yeah? All right. So 6 minus 6, just using a little algebra to simplify, 6 minus 6 cancels out, 0. And I get 4x divided by 4. 4 divided by 4 is 1, so those cancel out, and I do end up with x. So since the composition both ways yields x, I know that G and G inverse are inverses. All right, let's do one more example. Let's say I'm given Alright, so I'm given f of x equals 3x minus 2, and g of x equals x minus 2 over 3. And I want to use compositions to determine if g of x and f of x are inverses. So it doesn't matter which one I start with, which one I plug into what. So I'm going to start with f of g of x. I'm going to plug g into f. If you want to start the opposite direction, doesn't matter. Not going to make a difference. Okay? But I'm starting by plugging G into F. I'm going to do this composition. So I'm plugging G into X's spot. So I'll have 3 times, in X's spot, I'll have X minus 2 divided by 3 minus 2. Right? It's the entire function, just G of X is in X's spot. And I'll use algebra to break it down. So I have 3 times x minus 2 over 3. What happens to these 3's? They cancel out. And so I end up with just x minus 2 minus 2. Now what? Combine like terms, right? I have negative 2 minus 2, which gives me what? X minus 4. I did not get just plain x. And so I know that f and g are not inverses. I don't even have to go any further. It doesn't matter what g and f give me. I know that f and g are not inverses because f of g of x is not just x. Okay? We good? All right.